Hello everyone. Here we finish off the course with lesson 11, negative exponents, scientific notation, and polynomials. We know about exponential notation when we write something like 5 cubed or 5 raised to the third power. We know that the 5 is referred to as the base, and the superscript 3 is the exponent, which tells us how many times the base appears in the product. Now, when we're dealing with, so 5 to the third means 5 times 5 times 5 is 3 factors of 5. When we're dealing with variables, we have, for multiplying x together 4 times, we would interpret that as x raised to the 4th, and if we write it as x times x times x, it's expanded form. And now we get to some rules of exponents. And you could read the formalities, but basically the product rule for exponents states that when we multiply common bases, we add the exponents. So we even gave a little justification as to why that's true. And when you go through finding a product, you can only multiply the common variable factors. And so, although you could proceed in a variety of ways, one recommendation we have is to group those common factors together. So like in this example, where we group the y's and we group the z's, and then we went through to perform the product rule. So that's optional, but sometimes a helpful technique. Now here I'm going to rewrite the question, negative 9 y raised to the third multiplied by 7 times y raised to the 6th. You can simply jump right in and complete the problem, but what I'm going to do is to group the coefficients together, so negative 9 times 7, and group the y's together, y cubed times y to the 6th. And so then we can multiply the coefficients, we get negative 63, and using our product rule for multiplying common bases, we add the exponents and we get y to the 9th. So if you want to skip this middle step, that's fine, but sometimes that's helpful. We have the quotient rule, so just like multiplication was addition of exponents, for the quotient, subtracting exponents, so division is subtracting exponents. Give a justification through examples as to why that's true. And moving on to the pencil problem, again, in the example, you could read through and see how we again group things together. Optional, but sometimes helpful. And I'm going to rewrite the pencil problem here. 8 p to the 11th, q to the 13th, r to the 8th, divided by 4 p to the 9th, q to the 12th, and r to the 4th. So I'm going to choose to group all the common things together with using parentheses. You don't have to use the parentheses, but if this is helpful to see it. So 8 gets divided by 4, p to the 4th gets divided by p to the 11th, excuse me, gets divided by p to the 9th. Q to the 18th gets divided by q to the 12th, and r to the 8th gets divided by r to the 4th. So then we'll just do each one separately. 8 divided by 4 is 2. Each of these are quotients where we can use the quotient rule, dividing common bases. We subtract the exponents. So p raised to the 11 minus 9 is 2. Similarly, q raised to the 18 minus 12 is 6. And r raised to the 8 minus 4 is 4. So again, if you want to skip the middle step, that's fine, but sometimes helpful to use it. Then we have a power rule. So we have product, add the exponents, quotient, subtract the exponents, and now power, we're going to multiply the exponents. So if we see something in parentheses, which is referred to as a power, something raised to a power, in parentheses raised to a power, then we're going to multiply the exponents. And again, we give a justification. And we also stated the power of a product rule. So if you have a product raised to a power, you just simply raise each factor to that power and keep it as a product. Similarly, with the power of a quotient, if you have a quotient raised to a power, you take each factor, raise it to that power, and keep it as a quotient. So we showed a formal example here that you could read through. I'm going to jump right to the pencil problem. And a helpful idea is, again, I'm going to recopy this first. Try to focus a little better there. Okay, so we have 2, a raised to the 5th, b to the 7th, c to the 3rd, or c cubed, as a quantity raised to the 4th. So every factor inside the set of parentheses gets raised to this 4th power. So if you want to show it explicitly, 2 gets raised to the 4th, a to the 3rd gets raised to the 4th, b to the 7th gets raised to the 4th, and c cubed gets raised to the 4th. And then we'll evaluate each of those. 2 to the 4th is 16. Here, this is our power property, where we're going to, when we take a power raised to a power, we multiply the exponents. So a raised to the 3 times 4 is 12. Similarly, b raised to the 7 times 4 is 28. And c raised to the 3 times 4 is 12. And again, if you're proficient enough to skip the middle step, that's great. But when you see this for the first time, maybe it is helpful to show that middle step. Then we get into the concept of negative exponents. Basically, negative exponents mean reciprocals. And we don't really like to deal with negative exponents. So if you see a negative exponent, the idea is to change it to its equivalent reciprocal. So as we've shown, next to the negative 2, here's the general rule, x to the negative 2 can be written as 1 over x squared, so the exponent becomes positive. And we give a justification for this as well, that you could read through. And we could certainly, when we're faced with division of common bases, we could certainly use the division rule, or we could use the negative exponent rule to rewrite this quantity. And basically, if there is a negative exponent in the numerator, you could shift that quantity to the denominator and make the exponent positive. And similarly, if there's a negative exponent in the denominator, you could shift that quantity to the numerator and make the exponent positive. And then just deal with positive exponents. So in this example, we showed that where y to the negative 3rd was brought to the denominator as y to the positive 3rd, and y to the negative 12th that was in the denominator was brought to the numerator as y to the positive 12th. And then we proceeded with the standard division of common bases rule, where we subtract the exponents. And you can see our result y to the 9th. So that's a helpful technique, this negative exponent shift, if you will. And so in the pencil problem, I'll recopy. We're given x to the negative 4th over x cubed. You could proceed with the division rule if you want, but this negative exponent shift is helpful. See, x to the negative 4th, I don't like negative exponents, so I'm going to shift it. It goes to the denominator as x to the 4th. But this x to the 3rd that's in the denominator, I just have to leave that because that's a positive exponent, so that is fine the way it is. And what's left in the numerator is just simply 1. And now we can multiply in the denominator. So our rule for multiplying common bases is to add the exponents, so 1 over x to the 7th. Okay, the next thing now is zero exponent property. And anything raised to the 0 power is equal to 1 by definition. And we gave a justification for that. And then we talk about powers of 10, which lead us to the concept of scientific notation. And when we're dealing with powers of 10, the exponent tells us how many zeros there are in the expansion. For example, 10 cubed, or 10 to the 3rd, really means 10 times 10 times 10, which is 1,000. But when we get to the point where we talk about 10 to the 0, by definition, that anything to the 0 power is 1. Okay, here, let me fill this in. This is really 10 times 10, or 100. And this is just 10 to the 1st, it's just simply 10. But when we get to negative exponents, 10 to the negative 1st is really 1 over 10, which is 0.1. And 10 to the negative 2nd is 1 over 10 squared, which is 1 over 100, or 0.01. And 10 to the negative 3rd is 1 over 10 cubed. Remember the shift to get rid of the negative exponent, which is 1 over 1,000, which is 0.001. So one thing I just want to point out is that when you have a number, a power of 10 with a negative exponent, the number is less than 1, and if you have a power of 10 with a positive exponent, the number is greater than 1. So now to the concept of scientific notation. Turns out there's some really, really big numbers and in the scientific world, as well as some really, really small numbers. For example, the mass of the Earth. So 5.97 times 10 to the 24th kilograms, or the radius of a proton, a really, really small number. 1.535 times 10 to the negative 18th meters. We're going to convert these to back and forth from from scientific notation to standard notation, standard form. But scientific notation is always written in this fashion, where you have a number out in front of a power of 10. So as we wrote here in general, c times 10 to the nth power. So we can convert in both directions. Oh, I just wanted to point out, here's the mass of the Earth here. Look at all those zeros. Here's the proton. Look at all those zeros. Okay. So what our job will be is to convert between the two forms, between standard form and the form using scientific notation. And I think I'm going to do this particular video in 2 parts. I'm going to stop right there for now. we'll call this part 1, and then we'll come back and we'll do part 2 in a moment.